Welcome back to The Explainer. Today, we're cutting straight to the chase and looking right inside the mechanical heart of the legacy HPA SF6 circuit breaker. We're going to break down the puffer mechanism, pull ratings, and exactly how this piece of hardware survives the absolute worst electrical faults your ship can throw at it. Let's get right into it. Okay, so first up, the HPA puffer cylinder. Think of it kind of like a standard bicycle pump. But, instead of just inflating a tire, this thing is built to violently blast compressed, ionized gas straight at a highly dangerous electrical arc. And it does it to snuff that arc out in mere milliseconds. It's incredibly fast. And this analogy actually perfectly highlights why the HPA is just so effective. See, passive gas extinction basically relies on the ambient properties of the surrounding gas just sitting there, kind of hoping it cools the arc down. But the puffer mechanism, that is a mechanical gas blast. It actively forces that compressed SF6 gas directly into the arc, physically disrupting and quenching it. It doesn't just sit there and hope for the best, it literally fights back. So, during a fault break, here is the exact physical sequence of what goes down. Step 1. As the breaker opens, a moving cylinder compresses the SF6 gas against a fixed plunger. Then, step 2, all that compressed gas jets super rapidly through a specialized nozzle. And finally, step 3, it mechanically blasts directly onto the separating contacts, killing the arc instantly. It's a really brutal, forceful action, perfectly timed right with the contact separation. Moving on to pull ratings and real capabilities, pushing the HPA to its limits safely. 2,000 amps. That right there is the pull's real massive capability. Thanks to that active puffer mechanism we just talked about, the HPA can interrupt rated currents all the way up to 2,000 amps. That is an enormous amount of destructive energy being safely contained and, neutralized. But honestly, here is the most surprising truth about how this operates. You'd probably assume it takes some massive, crazy pressure to interrupt 2,000 amps, right? Well, actually, scratch that. It doesn't. It operates successfully at near atmospheric pressure. Seriously, it only requires a slight overpressure of SF6 gas to be present. It absolutely does not rely on huge, highly pressurized gas environments to keep your ship's network safe. So let's do a quick check for the engine room. Imagine you're standing there, looking right at an HPA pole. It shows SF6 is indeed present, but it's only at a slight overpressure, definitely not the full nominal fill. Suddenly, a massive fault hits. Can that breaker still safely uninterrupt an 1,800 amp fault? The answer, pulled straight from the operating specs, is a definitive yes. As long as SF6 gas is present at all, even just at a slight overpressure, currents up to 2,000 amps remain completely interruptible. The real danger threshold, the point where you actually lose that critical protection, doesn't happen until you hit the precise alarm pressure point, which is exactly 2.0 bar. So anything above that, and your ship is protected. All right, to wrap up our focus on the hardware itself, the HPA core mechanism is essentially a mechanical puffer cylinder that physically blasts SF6 right on the arc. And that exact action is what secures a 2,000 amp interruption capability at near atmospheric pressure. So you now understand its mechanical heart and exactly why its limits are so darn impressive. But of course, there's always a catch, right? This incredible puffer mechanism only works if the gas pressure aligns perfectly with the ambient temperature. So what happens when that engine room heats up? If you check the gauge on a sweltering day and it reads nominal, are you looking at a genuinely safe fill or just a really dangerous illusion? We're going to decode the exact pressure temperature rules you need to know in part 2 of this explainer, so stick around.